and welcome to the SCTE Expo 2023. We're here at Precision Optical Technologies booth. I'm joined by David Calhoun. He is the Technical Director of the Advanced Engineering Group at Precision OT. Dave, great to have you here.
Thanks for having me.
Can you tell me a little bit about yourself and your background?
Sure. So I've been with Precision now for over 6 years, and I have a PhD in integrated photonics from Columbia University. Historically, I've been involved in kind of the more forward-looking product development efforts within Precision, and specifically my subject matter expertise is in electrical and systems engineering. I am now serving as the technical director for our advanced group with a very capable team focusing on photonics design, embedded systems, and microelectronics to bring you these forward-looking products that we're going to demonstrate here today.
That's very impressive. So without further ado, tell me what you'll be demonstrating today.
Sure. So Precision's Advanced Engineering Group is currently developing a never-before-seen tunable 25 gig DWDM product with optical reach up to 40 kilometers. This product is enabled by a customized dispersion control ASIC, which is designed to extend the reach of traditional intensity-modulated direct detect transceivers. That is, by being built into transceiver designs that otherwise include commercial components. Our ASIC implements a combination of single sideband optical modulation and fully software configurable pre-compensating analog filter techniques to mitigate the effects of chromatic dispersion across all operating wavelengths from ITU 14 up to ITU 61.
Excellent. And so why is this ASIC technology important, and how exactly does it apply to 25 gig products?
Yeah. So while today's commercial 25 gig and tunable 25 gig DWDM products meet data rate requirements for the ever-increasing needs of access networks, they suffer from a nonlinear fiber impairment known as chromatic dispersion, which limits their ability to serve fiber deployments greater than about 15 kilometers without the use of external equipment such as dispersion compensating media or other complex architectures. Access network topologies, on the other hand, have primarily been established based on previous data rate requirements and on the capabilities of commercial 10 gig and 10 gig tunable products. Because chromatic dispersion gets worse with increasing data rate, the lesser 10 gig rate product can offer reach in the range of about 60 to 80 kilometers. So you need a scaling path from that. By extending tunable 25 gig reach to 40 kilometers, our ASIC solution enables a natural evolution from the existing 10 gig based architecture. So why don't you let me show you a demonstration of this product in action.
Yeah, let's see it, absolutely.
So here we have two of our tunable SFP28 transceivers implemented in a test set running a 25 gig Ethernet link. We're running through 40 kilometers of fiber, and on either end of that we've got thin film filter based MUX and DMUX. And as I said, we're running a 25 gig Ethernet link. On this MUX and DMUX, we've configured our two transceivers to be operating at the two ends of our conceivable ITU spec. One transceiver is running at ITU 20, one transceiver is running at ITU 60. And so we're emulating what a network provider might be doing from an upstream and downstream deployment perspective.
And so just question to follow up on that. Why is the chromatic dispersion effect so important for this particular upstream and downstream configuration?
Sure. So the challenge of chromatic dispersion is not only limited to specific fiber distances or data rates, it also varies based on the operating wavelength of the transceiver. Signals at the higher ITU channels, so toward ITU 61, are shorter in wavelength and experience overall less chromatic dispersion. On the other hand, signals at the lower ITU channels, so toward ITU 14, are longer in wavelength and experience more chromatic dispersion. Conventional 25 gig tunable offerings today use a method of optical chirping to compensate for this effect, but it's not wholly applicable to all operating wavelengths. You have diminishing returns across these wavelengths, and that limits performance to about 15 kilometers. Because our ASIC is configurable, it's possible to configure the transceiver and cater chromatic dispersion compensation to a specific distance and wavelength combination of interest. This capability can also be extended to normalize the effects of chromatic dispersion across all operating wavelengths, which greatly simplifies practical deployments. So here you can see this capability operating in our 25 gig Ethernet scenario at 0 BER. This 0 BER is enabled by forward error correction, just like all 25 gig products on the market today.
So then how exactly does this product interact with existing network equipment?
Sure. So this product is meant to be deployed in existing hub-to-node DWDM access network topologies, which require IP over fiber. This product is compatible with typical passives such as 100 gigahertz grid multiplexing and demultiplexing devices, as well as actives such as EDFAs. This configurable dispersion compensation can also be selected to work in tandem with fiber-based dispersion compensating modules if those are present on an existing network. So now you can start to imagine beyond 40 kilometers. All existing and upcoming 25 gig DWDM products, on the other hand, do require host side forward error correction, or FEC, and this product is no exception. To meet receiver sensitivity and link budget specifications, this product requires 25 gig Ethernet compatible FEC to be deployed in all host systems like switches, remote optical line terminals or OLTs, and remote PHY devices. So now what I will show you is some of the impact of what these signals look like going over the fiber, what happens to the ones and zeros of these digital streams. Here we have a second demonstration where we're showing just the transmitted signal coming out optically, going over 30 kilometers of fiber, and we are looking at what's known as an eye diagram, which is a representation of the ones and zeros, or the quality of the signal over time. And as you'll see from this interface, we're showing the signal is changing about every 5 seconds, and we're showing our case of configuring the ASIC to not implement our chromatic dispersion precompensation and to implement the chromatic dispersion precompensation. So this signal will change, and you'll see here there's no discernible difference between what would be a 1 level and what would be a 0 level. So you close. Now you have these open parts of the signal, which are open eyes in the eye diagram, where the difference between a 1 and a 0 is very clear.
What exactly does this technology mean for network operators across the globe?
Sure. So by bringing in our ASIC technology, we're easing some of the burdens, obviously, from a signal integrity perspective, making these signals operate better for the rest of the architecture that has to actually do something with that information. But also, our fully configurable ASIC-enabled solution works for both fiber access network deployments and upgrades, making those things simpler over time. Network operators can continue to use existing infrastructure, and since the product can coexist with all other DWDM 100 gigahertz channel space transceivers, network operators can depend on both backward and forward compatibility. Additionally, the underlying analog nature of our ASIC technology makes it applicable to both 10 gig and 50 gig IMDD solutions, offering operators more options for 100 kilometer performance in the 10 gig and a path to even more bandwidth at 50 gig access without the need for expensive or complicated coherent solutions.
There you have it. That is the demo for today. Thank you for joining us live. We'll be at SCTE Expo all of today. If you're around, stop by booth 565 to join us. Thanks, Dave, for your time.
Thanks, Alyssa.